So as we just discussed, melting points and boiling points are really strongly affected by intermolecular forces or intermolecular bonds. And keep in mind that this is something that's between many molecules. It's not just one molecule. We're talking about between molecules, and we're talking about intermolecular forces or intermolecular bonds. And stronger intermolecular bonds means that it takes more energy to separate those molecules. So if you have that Velcro ball, it takes more energy to pull those two balls apart than it would just to let them drift apart because they don't have that Velcro on them. So when you're looking at these things, I want you to imagine if you have a beaker full of that material, most of the time when you're seeing like a comparison between this melting point and another melting point, what you're seeing is one molecule. But that's not what is in that beaker. It's millions and billions and gazillions of molecules, and they're all interacting, but they usually have the same structure unless otherwise noted. Okay, so let's compare if you have a beaker that's full of something with London forces that's connecting it, and a beaker full of something that's hydrogen, got hydrogen bonding as intermolecular forces. Well, the one with the London forces is going to have a lower melting point and boiling point, and the one with the hydrogen bonding is going to have a higher melting point and boiling point. Now, we typically compare 2, 3, even 4 molecules, even more sometimes, to predict a trend. You do not have to predict the actual values of these melting points and boiling points. Nobody expects that. But what you do want to be able to note is that probably these things stick together more, and therefore it's going to have a higher melting point. And these things don't stick together as much, and they're probably going to have a lower boiling point. So when we go to compare these things, though, you have to compare apples to apples, which means that the mass of the compounds need to be similar. Not exact, but pretty much on point there, because shape and size also matter that we've already talked about. So larger compounds are generally going to have a higher boiling point and melting point. Now that gets really sticky when you have some molecules that are bigger and other ones can hydrogen bond, but we're not looking at that, so we don't really have to worry about it. So if we look at the same chart that we really were dealing with before, the highest melting point and boiling point is going to have the highest or strongest intermolecular force. And the lowest melting point and boiling point is going to have the least effective intermolecular force. So dipole sort of go in this range, and then we keep going up as we get to hydrogen bonding. And so we can compare that to the functional groups that we sort of categorized the other day. So if you have something that's an alcohol, it would be in hydrogen bonding, and alcohols therefore would have a higher melting point and boiling point than, say, a ketone would. That's right here. Okay, so let's look at some examples of these types of problems. We skipped too far ahead. There we go. So as an example, if you're looking at just exactly as I was about to say, an alcohol versus something that's a ketone, well, we have to consider the fact that this guy has hydrogen bonding, right? And this guy has dipole-dipole interactions. Well, dipole-dipole's great, but it is not as intense as a hydrogen bond. So that means that the alcohol is going to have the highest boiling point, okay? Why? Because it takes more energy to get those molecules to separate from one another. And when we're talking about boiling point, when we're talking about melting point, what we're talking about is average energy, because that's represented as temperature. The more energy you give something, the higher the temperature goes, and the more, the higher the boiling point. What that says is that takes more energy to separate those molecules because they like each other. They're stuck together really well. So that's something to consider when you're doing this, okay? Sorry, I've yet to figure out how to get it not to do that as I move. Next, we need to rank the compounds below from lowest melting point to highest melting point. And here, again, you're just going to identify, before you start anything, what are the intermolecular forces. So if I start further to the left, this is a ketone, and therefore it's going to have dipole-dipole interactions. Next, we have an alkane, so it's just London dispersion forces. Next, we have an amine, and this would be hydrogen bonding. And finally, we have a carboxylate. See how that has a negative and a positive that's hanging out there? This guy's just like the other part of the salt that's hanging out. So that means that this is an ionic bonded material. Okay. So that means that ionic bonds win. They're going to have the highest melting point. Next to that, we have hydrogen bonding. So that's going to be number 3. Dipole-dipoles would be by that, and then London dispersion forces. Now, if you started at London dispersion force and talking about how that's the lowest, fine, same thing, as long as you get the right answer here. Let me know if you have any questions here. Now, note that all of these are about the same size, about the same mass in the end. So, which one do you think of these two compounds will have the highest boiling point? If you said the one on the left, you're absolutely right. They have the same functional group in them. They have a ketone, but this first molecule is much larger and therefore will have a higher boiling point. Okay. As we sort of talked about with solubility, like dissolves like. That's pretty much what it boils down to, since we're talking about boiling points. Like dissolves like. And what that means is, on this entire chart, if things are closer to each other, then that means that they will dissolve in one another more easily. Now, I know that a lot of people see things as, will it happen or won't it happen? It's not a matter of a yes and no checkbox. It's a matter of how much of it will dissolve. You could probably get a teeny amount of table salt, NaCl, to dissolve in oil, but not very much. But you can get a lot of NaCl to dissolve in water. Okay? Same type of thing can happen with alcohols. You can have a lot of alcohols that dissolve in water very easily because they have the same intermolecular bond, right? Or intermolecular interaction. Things that are like oil, when you combine an oil that has London dispersion forces with water that has hydrogen bonding, those two things do not dissolve well. And it's because they're further apart on this chart. So that's what we mean when we say like dissolves like. So look at your functional groups, and it may be, as we get to see other things in the near future, we're actually looking at parts of a molecule instead of even the entire thing. So that's another thing to keep in mind. Okay, thank you very much.